Okay, well, welcome to our first makeup video for the days we missed last week. And for this, I'm just gonna, carry on where we left off on what day was it? Yesterday's video. Okay, so we were talking about the effects of different changes in condition on the position of equilibrium, meaning, which way will an equilibrium reaction shift, towards the right or towards the left, if certain changes are made. And for the previous changes, it's pretty straightforward which way the reaction will shift, because it shifts in order to relieve the stress. And it's pretty obvious how it does that. If you add extra of something, the reaction shifts away from that thing to reduce the excess. If you take something away, the reaction shifts toward that thing to replace it, and that kind of thing. But with the effects of temperature change, it's a little bit more subtle, because you have to know which direction of the reaction is endothermic and which direction is exothermic. Because usually if you see an equilibrium reaction written with a value for delta H, the enthalpy change, and of course, if it's negative, that would mean that the reaction is exothermic. And if it's positive, that means the reaction is endothermic. That value will be for the reaction moving forward, that is left to right. The enthalpy value for the backward reaction, remember, is the same number but with the opposite sign. And so if you're given a value for delta H, you can assume that whatever it is for the forward reaction, and then you can judge which way the reaction is going to shift based on that. So if the temperature is increased, that is, if you have more heat, then the reaction tends to shift in the endothermic direction. You have more heat, so it favors the direction it wants to take in heat, which kind of makes sense. If the temperature is decreased, that is, there's less heat around, then the reaction shifts in the direction of the exothermic direction. That is, if there's less heat around, then that favors the direction that wants to give off heat, because it's easier to give off heat if there's less heat already around. If you think about like running around, which way is it easier for you to stay cooler? If you're running around in the middle of the summer when it's 90 degrees with 90% humidity, or if it's running around on a day like this when there's snow falling outside my window, it's easy for you to keep cool. In other words, give off your body heat to the environment when the environment is cool than it is when the environment is hot. And it's kind of the same idea with equilibrium reactions. So if the temperature goes down, that favors the direction that wants to shrug off heat. And keep in mind, in this case, that changing the temperature, unlike the other changes we had been talking about, changing the temperature also changes the value of the equilibrium constant. So there's that to think about too. And this is what I mentioned before a moment ago, that if any delta H is stated for the reaction, then you assume that that value is for the reaction going left to right as it's written. Okay. And another way to think about this is, if you remember back when we were talking about thermodynamics, we said that in a chemical reaction that takes in or gives off energy, you can think of energy or heat as a reactant or a product. So in an exothermic reaction, the heat is a product. So like in this example here, carbon monoxide plus 2 hydrogens yields methanol and heat or energy. And the delta H is minus 91 kilojoules. And the fact that the delta H is negative tells you that the reaction is giving off heat, or in other words, heat is one of the products of that reaction. And if you increase the temperature in which this reaction is being done, then that's like providing more heat. In other words, you're providing more of one of the products, and so the reaction will shift away from that direction. Just like it does if you add more of methanol, it would shift to the left. And on the same, by the same measure, if you were to decrease the temperature, that is, take away heat, then the reaction would shift to the right to replace the missing heat, more or less. Just as it would shift to the right if you took away some of the methanol, it would shift right to replace it. In an endothermic reaction, okay, the reactant is, heat is one of the reactants. You have to put heat or energy in order to get a reaction. And so in this case, 2 SO3s plus energy or heat will yield 2 SO2s and 1 O2. The delta H here is positive. That's another sign that it's an endothermic reaction and it's taking in heat. And heat is, again, like a reactant, although we don't usually write heat in as a reactant, but it's like a reactant. And it acts like a reactant in Le Chatelier's principle too, because if you add more heat, then you're adding more of a reactant and the reaction will shift away from the excess, just like if you added more SO3. And if you take away some of the heat, the reaction will run backwards toward the direction of the heat, just like if you were to take away some of the SO3. Okay. So that's kind of an easy way to reason it out, so you don't have to necessarily memorize it. Okay. And okay, there's a table that summarizes changes in temperatures on page 691 that you can have a look at. The example for this sort of thing is this equation here, where you have Cl2 plus 2 NOs yield 2 NoCl2 and heat. I kind of squeezed that in because the book didn't actually write that in, but I'll write it in. It does tell you that the delta H, though, is less than 0. And if the delta H is less than 0, that's another way of saying it's negative, or in other words, the reaction is exothermic. So temperature increase, and it wants to know what happens if the temperature is increased. And a temperature increase means more heat. Heat is like a product in this case, so the reaction will shift away from the heat, which means backwards. It'll go to the left. And that's the endothermic direction, because again, if the forward reaction is exothermic, then the backward reaction is endothermic. And you'll end up with more reactants and less of the product. And the result of, since we're changing temperature here, the change is going to be in the equilibrium constant. So we actually are changing the equilibrium constant here. And in fact, the equilibrium constant will be smaller at lower temperature, or sorry, at higher temperatures for this reaction, because you're going to have more reactant and less product. Well, K, of course, is product over reactant. So if you have more reactants on the bottom and less product on top, K will be smaller. All right, so the direction of the reaction shift. Well, because above what you've got is a situation where the reaction quotient is greater than K. And we already mentioned that the reaction is going to shift to the left. Okay, how is the partial pressure of each gas change? Well, as I said, you're going, if the reaction shifts backwards, you're going to have more chlorine and more NO and less NoCl2. So the partial pressure of chlorine and NO2 will go up, and the partial pressure of NoCl will go down. Okay. And the last thing in the chapter to discuss here is the effect of catalysts on equilibrium. And this is the fun part, because it turns out catalysts have no effect on equilibrium. Because catalysts, well, remember, catalysts provide an alternative mechanism for the reaction to occur by, which requires less activation energy. And that makes, because the activation energy is smaller, that means that the reaction goes faster than it otherwise would without the catalyst. But it turns out the catalysts have an equal effect on the activation energy for the forward reaction and the reverse reaction. And so the equilibrium actually doesn't shift. Remember back to the beginning of the chapter where we said that the equilibrium constant is essentially the rate constant for the forward reaction divided by the rate constant for the backward reaction. Well, if K1 and K minus 1 change by the same factor, then the ratio ends up being the same. You know, like if you double them both, then the result though is going to be the same. Like, you know, 1/2 is the same as 2/4. That sort of thing. So that's pretty simple. Catalyst, no effect on equilibrium. Okay, and that is the end of chapter 15. Since we're only about 10 minutes into this video, we will go ahead, assuming I can find it, and go on with chapter 16. Okay, and I will have to get the homework problems for chapter 16 up on Achieve as soon as I can. Chapter 16 is about acids and bases. And we've already done a couple of lab experiments dealing with acids and bases, in which I've had to introduce already some of the basic properties of acids and bases. So hopefully you'll remember some of that, and this will be a handy review for that kind of thing. And so first, a little bit of introduction as to what acids and bases are, or where we might know them from, because acids and bases are actually quite commonly encountered in everyday life. Some of the properties of acids and bases involve the way they taste. Now, you want to remember not to taste any acids or bases in the laboratory, but in real life, there are lots of foods and lots of other substances we encounter that are acids or bases. And one thing that acids have in common is that they taste sour. And it turns out people like sour things. And so a lot of foods we eat are acidic. And that would include things like citrus fruits, oranges, lemons, limes, things like that. They all have citric acid in them. And vinegar, which has acetic acid in it. And of course, there's vinegar in ketchup too, so that's acidic. And also things that we don't eat, like toilet cleaner and stomach acid. Well, stomach acid, you don't eat it, but it's in your stomach. That is actually hydrochloric acid. And aspirin, if you've ever tried chewing an adult aspirin, you'll know that they are extremely sour. And that's because it is an acid. It's acetyl salicylic acid. Now, of course, there's also battery acid in the lead acid battery in your car. That's sulfuric acid. And there are lots of other acids and bases too. Also. Bases, on the other hand, there are not very many basic foods because bases taste bitter, and most people don't really like things that taste bitter. So you don't find bases in a lot of foods. But bases are really good at cleaning things. They're good at, say, cutting through grease and oily dirt and things like that. So they're used a lot for cleaning. So things like bleach and ammonia and borax and soaps are all basic. If you've ever gotten soap in your mouth while taking a shower, you know that it tastes pretty bitter. And that's because it's basic. Also things like pool chlorine, which I put in quotation marks because the little tablets you put in the pool are not actually chlorine, as you might wonder if you thought about it, because of course chlorine is a gas and those little tablets are solids. So how could that be chlorine? Well, the answer is it's not. Actually, it's sodium hypochlorite, which is actually bleach. If you dissolve sodium hypochlorite in water to the right concentration, you have chlorine bleach. And they so that basically what you're doing is turning your pool into a really dilute bleach. And in fact, you can use bleach in the pool if you run out of pool chlorine. And it's the same stuff. It's actually sodium hypochlorite that has the formula NaClO, and it's a solid in its pure state, but it dissolves well in water. They call it chlorine because it has the same effect as chlorine gas would have if you dissolved it in water. The reason they don't actually try dissolving chlorine gas in water is that chlorine, being Cl2, is a nonpolar molecule, and water, of course, is very polar. So if you try dissolving nonpolar CO2 in polar water, most of it, about 95% of it, is going to come bubbling back out and kill everybody in the vicinity. So they're smart enough not to do that. What they do instead is they dissolve sodium hypochlorite in the water. And most of that stays in the water, although some of it does come out as chlorine gas, which you can smell. That smell that you smell when you open a Clorox bottle is chlorine gas coming out. And of course, you can smell chlorine around pools too, but that's just because the sodium hypochlorite in the water is breaking down to produce a little bit of chlorine gas. Of course, also antacids like Tums or Alka-Seltzer, those are bases. Baking soda, I forgot to put that in here, but sodium bicarbonate in baking soda, which also can be used as an antacid, by the way, is a base. And also a lot of cleaning products like Drano. If you look at the ingredients in Drano, one of the ingredients in Drano is sodium hydroxide, which is a very strong base. And that's that's why Drano is so good at cutting through, like greasy agglomerations in your drains, because that's the kind of thing that bases are good at. What actually makes an acid or a base is what they do when you put them in water. And what they do is ionize. And acids ionize to give off their characteristic H+ ion, and bases ionize to produce their characteristic OH- ion. And so that's something that all acids and bases have in common, is that when you put them in water, they always ionize to some extent. They may not ionize completely, but they ionize to some extent. The first scientific acid-base theory, now acids and bases, of course, have been known, and a lot of their chemical and physical properties have been known for thousands of years. But it wasn't until about 1885 that a Swedish chemist by the name of Arrhenius actually sort of identified the key scientific factor that caused acids and bases to behave the way they do. And Arrhenius defined an acid as something that ionizes in water to produce H+ ions, or a proton, because remember, an H+ ion is a proton. A hydrogen atom, just H with no charge, is nothing but a proton and an electron. And if you therefore have an H+ ion by removing the electron, that's just a proton. So H+ and proton really mean the same thing. The proton then attaches itself to a water molecule, and you get H3O plus the hydronium ion. And so a lot of times in dealing with acids and bases, we'll actually write H+ to represent the ion that's coming off the acid, even though ultimately, because it's happening in water, H3O plus would be actually more accurate. But it's easier to write H+. Bases, according to Arrhenius, are compounds that ionize in water to produce hydroxide ions, OH-. And acids and bases are essentially the opposite of each other, because if you take an H+ ion from an acid and an OH- ion from a base, they will come together to form water, which is neutral, right between being an acid and a base. So, like basically acids and bases are the opposite of each other. Okay, so for a little more detail on ionization of acids, acids ionize in one. This is an interesting thing, actually. Acids ionize in water, even though they're not ionic compounds. Acids are molecular compounds. Acids consist of H+ and an anion, negative ion. And sometimes there's more than one H+, so I'll call it H+ and an anion. Well, when we defined what an ionic compound is, we said that an ionic compound has to involve a metal, unless it involves the ammonium ion. That's the one exception. But ionic compounds involve a metal and a polyatomic ion, or a non-metal anion. And there's no metal in the acid, so it's not an ionic compound. But it acts like an ionic compound when you put it in water. So that's an interesting thing right there. So the formula for an acid will normally begin with H, and there will be a certain number of them. So I put a little X there to represent that there might be more than one, followed by the formula of an anion. That's for the inorganic acids. This book tends to write the formulas for the organic acids like that also, and you can write them that way, but also the formulas for organic acids, that is, acids that contain hydrogens and carbons, can be written a different way, in which the formula ends in the letter COOH. And in this case, well, in the case of inorganic acids, it's only the hydrogens at the beginning that can ionize in water. In the case of the organic acids, though, it's the hydrogens at the very end in the COOH group that can ionize in water. And the reason that it's often written this way as COOH is because in organic chemistry, there are a lot of different molecules that have the same molecular formula. And the difference comes down to how they are arranged. That's what really differentiates one from another. And how they behave depends on things called functional groups. And this COOH happens to be the carboxylic acid functional group, which is what makes an organic acid an acid. And it's actually arranged as like this: C double bond O, single bond OH. And this will be on the end of the molecule. And on the other end of that, you'll have other hydrogens and carbons. And so if you see COOH at the end of the molecule or the formula, you'll know right away that you've got an organic acid. And that is something that you otherwise might have to sit down and figure out if the formula were written in some other way. Okay, so we can look at the ionization equations for a couple of acids. And we see that for strong acids that dissociate fully, there are only about 6 or 7 strong acids, but they are very important because they're very commonly used for acid-base reactions. And one of them is hydrochloric acid, or HCl aqueous. Remember, in order for it to be an acid, it has to be dissolved in water. Pure HCl is a gas, and it's called hydrogen chloride because as a gas, it's not acidic. It's only when it's dissolved in water that it's called hydrochloric acid. That will ionize into H plus and Cl minus. It is a single direction arrow because for strong acids, they ionize completely. And so this reaction goes to completion. If you put some hydrogen chloride gas into water, all of that hydrogen chloride will ionize and basically become hydrochloric acid and will immediately ionize into H plus and Cl minus, and there will be no intact HCl molecules left. This is the simplest way to represent the ionization. Sometimes we prefer to include the water in the ionization because, as I said, once the H plus is generated, it tends to grab onto an H2O. And so if you want to include the H2O in the ionization equation, you can write it as HCl plus H2O yields H3O plus, which is an H2O with an H plus attached to it, plus Cl minus. Either way, though, it's only a one-way process. This is a reaction that goes to completion. Okay, on the other hand, for weak acids, and a weak acid is anything that's not a strong acid, really. There are about 6 or 7 strong acids, and all of the other acids, thousands and thousands of them, are considered weak acids. And so all you're going to have to do is remember the list of strong acids, and anything else you can consider weak. And hydrofluoric acid, as it turns out, is a weak acid. Like with HCl, pure HF is a gas, and it's known as hydrogen fluoride, but it dissolves readily in water, at which point it becomes an acid, and it's known as hydrofluoric acid. And it will dissolve or ionize into H plus and F minus, the fluoride ion. But because this is a weak acid, the dissociation is not complete. It is, in fact, in equilibrium. So we have the double-headed arrows. And that means that there will be an equilibrium constant for the dissociation of weak acids. And we discussed that in lab. That equilibrium constant is known as Ka. And we will get to it in a little while. But anyway, just as a reminder, weak acids only dissociate partially, and the reaction is, in fact, in equilibrium. If you want to include the H2Os in the equation, then you could write it as HF plus H2O yields H3O plus F minus. But again, still an equilibrium reaction. The dissociation of the strong acids makes things really easy because in a situation like this, if you want to know what the H plus is, what the H plus concentration is, I mean, it's the same as the original concentration of the HCl, because all of this becomes this. With weak acids, it's not so easy because not all of the HFs become H plus and F minus. So the H plus concentration, whatever it is, it's going to be quite a bit less than the original concentration of HF. And we're going to have to use the Ka, or the equilibrium constant, for this reaction to find out what the H plus concentration actually is. Or we just measure the pH, one or the other. Okay, so as I said, when you put strong acids in water, they completely ionize 100%. And that means that any strong acid in an aqueous solution will consist of nothing but ions. So you put HCl in water, you're going to get H plus ions and Cl minus ions. You're not going to have any intact HCl left. And the same goes for all of the other strong acids. And here are the strong acids here: HCl, or hydrochloric acid, HBr, or hydrobromic acid, HI, or hydroiodic acid, HNO3, which is nitric acid, H2SO4, which is sulfuric acid, HClO4, which is perchloric acid, and HClO3, which is chloric acid. And that's all for the strong acids. Everything else is weak. Okay. So the formula only indicates an acid, though. You want to look for the H up front or the COOH at the end. And that's because most hydrogen-containing compounds are, in fact, not acidic. There are lots of compounds out there with lots of hydrogens in them that are not acidic. So you got to look either for the H at the beginning of the formula or the COOH at the end, and then it'll be an acid. Okay, so the question here wants us to write the ionization reaction for perchloric acid, HClO4. That's a strong acid because it's on the list I just gave. And so HClO4 aqueous will yield in a one direction arrow, H plus ClO4 minus. Or you could do it as HClO4 plus H2O, yielding H3O plus ClO4 minus. So you could do it that way. Each of these is equally correct. And the question next is, what is the H plus ion concentration in 0.0015 molar HClO4? Well, it's the same, because every one of these molecules will dissociate into H plus and ClO4 minus. So however many of HClO4 molecules you had to begin with, you end up with that many H plus ions. And assuming the volume hasn't changed, it'll be the same concentration. Okay, you can actually kind of prove it by setting up a table where you look at initial concentration and final concentrations, or sorry, initial change and final concentrations. This is sort of like an ice table, only it's for a reaction that goes to completion. And so if you start with 0.0015 molar HClO4 and no products, then the change, because this reaction goes to completion, should be for you, the change should be basically losing all of the reactant. There's only one reactant here, so there's no problem about which one is the limiting reagent or anything like that. You lose all of it. And since the reaction is 1-to-1 in the stoichiometric ratios for everything, that means that you gain the same amount of each product. Okay, so for the H plus, if you started with 0 and you gain 0.0015, then 0.0015 is what you end up with. Okay. And that wants us to write the ionization reaction for HNO3, or sorry, HNO2. Came out looking like a 3. HNO2, that's a weak acid. So HNO2 aqueous will yield in an equilibrium reaction H plus NO2 minus. You could also write this as HNO2 plus H2O, yields H3O plus NO2 minus. That would also be correct. And you notice how they didn't ask us what the H plus concentration for this reaction is, or for this substance is. It's because we don't have any way of knowing without having more information, because this is not a complete dissociation here. Some of the HNO2 molecules will dissociate into H plus ions and NO2 minus ions. Most of them do not. So we don't know exactly what the H plus concentration is. Even if we knew what the original HNO2 concentration is, we still wouldn't know what the H plus concentration is, except that we would know that it's a lot less than the HNO2 originally was. Okay, and that's what this is saying down here. But they did put in a fourth part of the question. It says, how would H plus ion concentration from a 1.77 molar HNO2 solution compared to that from a 1.77 molar HNO3 concentration solution? Or sorry, HClO4. Yeah. Well, the difference is HNO2 is weak and HNO3. Oh no, sorry, it was what? Was that HNO3 or was it HClO4? Oh yeah, it was HNO3. HNO3 is strong, HNO2 is weak. So for HNO3, as long as there's only one hydrogen in the molecule, the H plus concentration will be the same as the original concentration of the acid, 1.77. For the HNO2, that's a weak acid. Most of the molecules do not dissociate in water, so you only get a few H plus ions. And so the H plus concentration for HNO2 will be much less than 1.77. So the concentration, H plus for HNO2 is much less than H plus for HNO3 if the concentrations of the acids are the same. And then the next question is basically asking the same thing, only with HClO4, which is strong, versus HClO, which is weak. It's also important to remember when talking about acids and bases, and sometimes even the books themselves make this mistake, but strong acid and versus weak acid has to do with percent dissociation. And whether the reaction is, or whether the acid is concentrated or dilute, those are completely separate considerations. And those have to do with concentration. So you can have a weak acid that's very concentrated, and you can have a strong acid that's very dilute. That's entirely possible. So strong versus weak is entirely separate from concentrated versus dilute. All right. Having said that, I think we're about halfway through the video now, so we can sort of stop the clock and stop the video, and I'll be back with the second part in a moment.